was to update our rolls method for our dice object such that instead of it creating a sum of all of our rolls, it returned an array containing the individual rolls. Correct? All right, how'd that go? Not too bad? All right, so at the end of class last time, we were looking at creating arrays. So up here, we created an array of 10 elements, filled it up with some random numbers. So here's us filling it. Here's us changing one element of it. Then here's us printing it out. So we had the basic tools. We'll talk more about arrays today in the context of pass by value versus pass by address. And we've recently done that with objects as well. So we were going to come in here and we were going to change our roll method. So let's just change this guy for the number of times that we're going to roll. And if we're going to roll the dice 5 times, for example, we're going to need a 5-element array. So we're going to build a new array in here. And this guy's no longer going to return an integer. It's now going to return an integer array. Okay? So we're going to build an integer array in here. We'll call this guy maybe the rolls. This guy will be a new integer array of size times for the number of times we're going to roll the dice. All right. Now, our for loop here that goes through just happens to take I on a voyage between 0 and times -1. Well, arrays are indexed. They're 0 indexed. So the first time through, I'm going to set the rolls at bucket I equal to that roll. The next time through, I'll set the rolls at bucket I to the next roll, so on and so forth. So I'll go ahead and I'll get rid of my sum. We'll get our current roll. We'll get the absolute value of that roll. Then we'll whittle that roll down to something of the correct size. And then we'll go ahead and say the rolls at bucket I equals that new roll. In the end, we'll return the rolls. All right, so that was the modification for the homework assignment. Create a new array big enough to hold all your rolls. Create your rolls. Add each roll to the next bucket of the rolls. So in this case, we're actually dual purposing this variable I. We're using it to keep track of how many rolls we've done. And we're also using it to index where we are inside of the roll method. If you didn't like using that for multiple purposes, you could have always created another variable like int pos, started off at 0, set the rolls at bucket pos equal to cur roll, and then pos plus plus. You could have kept 2 separate variables for indexing where in the array you were. Does that make sense? Okay, so now let's look at this a little bit. So I'm going to go ahead and get rid of this. We'll go ahead and create an instance of our dice class. So we'll say dice D is equal to new dice. And we'll make this guy a 6-sided die. And then we're going to say int array result is equal to D dot roll. So here's our roll version that returns the integer array. And we'll go ahead and have it roll 5 times. And then I'll do a system.out.println result. What's this guy going to print out? Memory address. All right, so there's our crazy memory address. Notice how the virtual machine gives us a little naming convention. So this is an array of integers at this memory address. So we can actually look at the memory address from the Java virtual machine and get a little bit of the identity of what actually lives there. That's not something we can always rely on in programming languages. This has more to do with the Java virtual machine setup of things. All right, so now if I actually want to see the contents of that guy, I'm going to have to spin through and view it, right? So maybe we give ourselves a little static method, print array, and this guy takes in an integer array as a parameter. And we go through and just print out all the elements in that array, maybe just so they're kind of next to each other. Maybe we put tabs in between them, something like that. So we're going to go ahead and we're going to say for int I is equal to 0, I is less than, how many elements are in AR? How many elements are in AR as far as I'm concerned right here when I'm writing this function? AR.length number of elements, right? So I'm going to pass some array to this guy. We can use this for a whole bunch of different stuff. So AR.length number of elements. Now notice this guy is not a function like strings have. So it's not the length method, it's actually a length field. It's just a variable, but it holds the same kind of information. It just resolves it in a different way. Then I++, and then we want to go ahead and just for visual sake, we're going to print it all on one line. So instead of kicking it down a line where we have a whole bunch of stuff, all one per line. So we're actually going to use the other version of system.out.print called system.out.print instead of println. And we're going to go ahead and print AR at bucket I, and then we're going to concatenate onto that a tab. Did we look at tabs last semester? Okay. So first of all, one interesting thing we should notice here is you see single quotes here. What do single quotes mean? It's a char. And what are chars? Okay, it's a primitive type. It's a signed integer. But when we think of chars, we think of it as a single element, right? A single character from the Unicode character set. I have two things in here, though. Why is that okay? Yeah. So this guy right here, this backslash, is the escape character. And so it's giving some meaning to this guy. This is not the character T. This is the escape T. This is the tab character. Okay, we have several of these. We have \n, which is a line feed. We have \r, which is a carriage return. On Windows, \n comes with a carriage return. On Mac now, it also comes with a carriage return. Some older Unix systems, \n does not come with a carriage return. You would have to do both of them to actually kick it down a line and then feed the line. That's more of a older kind of something left over from the late 60s. All right, so those are just some of our common escape characters. So I'm going to throw a \t in there. So that'll give us a number, and print does not kick it down a line. And then we're going to tack onto it the tab. Now, this is only going to be really meaningful for us for a couple more weeks because we're kind of, sneaking up on midterms, right? And after midterms, we're transitioning our Android skills over to writing, our Java skills over to writing Android applications. So we're not going to have text-based output for all that much longer, okay? Now, that doesn't mean that a tab never comes in handy. You might want to format some text that shows up on a label or something like that, in which case you might want to have some equidistant spacing in it. But, this whole text-based output type thing, this is something that is kind of historically relevant for programmers, but also still pretty relevant for IT professionals, the programmers in that field, because those are people that aren't necessarily writing software that's going to have this nice graphic user interface. It's not going to run on a cell phone or run on a desktop computer. It's running on the Linux operating system sitting on some switch under the floorboard somewhere. That makes sense? So this kind of goes back to this argument I made early in the semester where a common belief in the program is that computer science traditional equals programming, IT equals not programming. Where I can make the argument that the IT professional actually has the more difficult programming job. Because the computer science person, they have these nice tools made for them with a lot of drag and drop crap that we're going to see in Android where we can just throw a button on there and voila, we're good to go. And you don't have those kind of tools when you're writing, backup scripts and stuff like that on some switch that doesn't have a user interface, or at least doesn't have a friendly user interface. All right, so now after we've gone through this for loop, ar.length number of times, we're going to kind of be stuck at the end of that last line. So we want to go ahead and just kick it down a line. System.out.println. Now there actually is a version of println that takes no parameters. I usually just like printing out the empty string. Kind of solidifies that idea of I'm printing nothing. But println says go ahead and kick it down a line. Make sense? We also could have incorporated it in here if we wanted to be, we've looked at inline if statements before, right? Let me show you the syntax for it. If I chose not to do this, I would not recommend writing it this way, but it is a possible way of writing it. So I can ask the question, I equal ar.length minus 1. If that's true, give me a carriage return. Else, give me a tab. Have I shown you something that looks like this before? I think I did. So this is called an inline if statement. This says, if this is true, boil down to this value. Otherwise, boil down to this value. So with this in mind, I'm actually building in the carriage return on the very last time through here, building it into the logic, so I don't actually have to do a println afterwards. Does that make sense? But I would still say this would be relatively poor programming practice for the modern programmer. This is something that most modern programmers, unless they happen to come out of a C or a C++ background, isn't going to be very familiar with, this inline if statement. And it's also, I think, kind of bad programming practice. It kind of falls into a similar vein as that we've talked about the I++ or the plus I, the plus operator. How technically plus I means something different than I++. And if you really understand that, you can use those guys in line. But you're never wrong if you just put the increment on a separate line. Nobody's impressed if you write your code with 3 fewer lines. All right, make it easy to understand. And this code like this doesn't digest visually as well as it might, right? This is a little bit difficult to look at, let's say. But we'll go ahead and we'll run it this time so you see it work. So we'll say driver dot, what I call it, I'll print array. And then the array I'm printing is result. All right, so we'll call our print array. It'll print out result. Just to show you that it did kick down a line. System.out.println. Just throw an LOL in there. So this LOL should be on its own line. Go ahead and run this guy. What row? That's interesting. Where are all my roles? So this guy is going to boil down to a number. Is it doing math with that? I think it might be doing math with that. So even another reason to not write it this way. We just take this out real quick and make sure we have the right values. Yeah, those are our values that are there. If we concatenate onto that a bunch of tabs, there's our values with tabs on it. Then we do the kick down a line. That kicks it down a line. That is actually interesting that it, when I had the inline if statement here, this boiled down to either a carriage return or a tab each time through. It's giving us the characters are there. It's giving us the empty Unicode characters. because it's adding to it these characters it doesn't know how to display based on adding a number, that is the Unicode value of this, onto the position of this guy. So not a great use for this anyways. But we'll keep the tab in there. This is easier to read code anyways. So there's our numbers. We do want to add. It should have the tab on it. So let's print this guy concatenated with it just showed up with a space a second ago, didn't it? Oh, I did this? Oh, so it's doing the math anyways the other way. So with that in mind, then we should be able to do this. If I go in here and I say boil down to this string versus boil down to this string, then we're guaranteed that this will be concatenation because these guys are strings. And I shouldn't need to do this. I think this would need to be the N. Well, still doing it. There we go. That's very strange. It didn't treat this guy as a statement in and of itself. We had to surround it in parentheses in order for it to treat it as an inline if statement. But that is interesting to me. Oh, actually, it's not interesting to me. It does make sense. If I do that, let's just look at this real quick. Let's do the empty string. We intend this to be treated as the concatenation operator, right? But that guy could be one of two operators, concatenation or addition. Now, when is it treated as the concatenation operator? Under what circumstance is the plus sign treated as concatenation? Yeah, when one of the sides is one or both of the sides is a string. What's this dude? He's an int. What's this dude? Char, yeah, which effectively is a signed integer. I don't have any strings present, so it's doing math with this number, which is some number between 0 and, well, actually 1 and 6 in this case, based on what we're calling, and the Unicode numeric of \t, which I don't know what that number is, but some value on the Unicode character set. And it just happens to be a value that isn't displayable inside of Eclipse's terminal. So a terminal needs to be compliant with a character set. And I think Unicode is ASCII compliant, but actually only for like a certain subset of ASCII. So different terminals can show different things. So like our terminal in here can't show like the smiley faces and things like that. Things like that show up as like question marks in here. Well, these are showing up as blank spaces. If we took it out to the terminal out here and ran it out here, we can go into preferences on this terminal. And there is a profile there's a setting in here. We can choose how this terminal should act. Yeah, for encodings. So we can choose 32-bit or 16-bit Unicode, so we can choose the different things we want it to adhere to for the terminals, for what it knows how to output. So these are all the things it supports. Okay, so in any case, roundabout way, questions about the homework assignment? And I'll still give the plug that we probably don't want to use the inline if statement. Every now and then it becomes handy, but more times than not, it gives you some weird output. We saw there, we had to surround it by parentheses, that kind of stuff. Okay, and then in this case, if we want this to be treated as concatenation, we needed one of the sides to be a string, so it'll work now. Make sense? And there's our individual roles. We wanted 5 of them, so here's 5 roles. We run this multiple times, we should get different roles. Okay, so now let's talk about arrays in terms of pass by value versus pass by address and really understand how arrays work. So when I create an array, int array AR is equal to a new int array of size 5, something like that. Okay, that's creating a place in memory. Now, for right now, actually, let me just go back here to this. We'll go ahead and print the stuff out real quick. So we'll print it out. Then I'm going to have a function called static void changeme. This will take in an int a or whatever. And we'll say a is equal to -1 system.out.println a. Up here we'll say int val is equal to 5. And just for this example, I'm going to just comment out that line, so we won't actually print the contents of an array. We're looking at something else here. So I'll have an integer val equal to 5. We're going to go ahead and print that guy out. All right, so that'll print out a 5. Then we're going to go ahead and we're going to call changeme, driver.changeme. We'll go ahead and pass val into that guy. Val will come in, so in this case, a will be 5. We're going to set a equal to -1. It should then print out -1. We come back out here. We print out the value of val. What should print out there? -1 or a 5? We looked at this, I think, early last week when we first looked at objects. So I'm going to have 3 different printlns here. I'm going to have, here's one here. There's one inside of changeme, and then here's one outside of changeme. What's the output of this program going to be? What do you think it's going to be? 5, -1, 5. Anybody disagree with that? So because you know the answer's right, or you're afraid to disagree with her? So it is going to be 5, -1, 5. Now the question is why is this one a 5? How'd you come to that conclusion? Okay, well, I could have named this guy Val instead of A. Would that have made a difference? Why not? You're right. We're not, I mean, we are changing this guy, but we're changing him locally. And what does that tell us about how this value is being passed in? By pass by value. We're getting a copy of that guy. Okay, so we're getting whatever val is. We're saying, here's a copy of me. It will come in here. We're changing that copy, printing out the modified copy. But when this method dies, we are now back to the old val, the original scope of val. That makes sense? So everybody's good with that one? All right. So now I'm still not going to print out my array, but we know that this array is going to be filled with values between 1 and 6. Right? We're guaranteed that. We've seen that enough times that we're comfortable with that. So I'm going to go ahead. We're going to get rid of this int val. I'm going to print out my array at bucket 0. This guy is going to take in an integer array. I'm going to change bucket 0 of that array to -1. Then I'll print out bucket 0. And I'll come back out here and print out bucket 0. Now, what kind of value lives at bucket 0 of my array? What kind of value? It is a roll, but how do we represent rolls? As an integer. So is it any different than our int val? An integer is an integer. Okay. So what's the output of this program going to be? You can't give me an exact answer for this first guy, but you can give me a rough answer. So what's the output of this line going to be? Some number between 1 and 6. Okay. Then we call driver changeme, passing in result. That comes in here as an integer array. I change bucket 0 to a -1. What's going to print out here? -1. All right. Now we bounce back to here. What's going to print out there? Think a -1 or the same value between 1 and 6? So I wouldn't be using this as an example if there wasn't a difference between the previous thing. That's your logic breakdown. All right. Well, you're right. So this guy does give you a -1 in this back thing. So what does that tell us about how arrays are passed? Passed by address. Just like objects are passed by address, unless they're strings. Okay? So arrays are passed by address, which means when we made this change here, we got a pointer. If I were to print out A here, as he pointed out at the beginning of class, we get a memory address, right? And we're going to get the same memory address here if I go ahead and print out A in here, and I print out result out here. Even though these variable names are different, we know they're actually synonyms for each other. So we should see 2 crazy memory addresses that are identical to each other. That's A, that's result. There's our evidence of pass by address. We're working with the actual address of that array inside of here. That makes sense? All right, so important rule of thumb, when arrays are passed around, they're passed around by address. So any changes you make to that array will be permanent changes. Now, let's look at our slides, and I want to talk just for a few minutes. I think we did look at this last semester, but I want to review it quickly when we talked about lists in Python. I want to talk about how arrays are actually built. So when I say int array AR is equal to a new int array 5, something like that. The new keyword, we said this is kind of like our real estate agent, right? Goes and gets us some new memory. All right, so that's the guy that creates the crazy memory address, talks to the operating system and says, yo, Windows, or yo, Mac. Actually, it talks to the Java virtual machine and says, I need enough memory to hold this many of those guys. Make sense? 5 integers. How big is an integer? Not overly important, you know this, but you should be ballpark. You should probably bounce back and forth between 2 values. That's a byte. So we have byte short, int long. So we went from 8-bit to 16-bit, which is our short. 32 bits are our integers. Okay. Now, the thing is, the reason why that's maybe not super important you memorize is because that answer might change in 5 years. You know, right now it is still a 32-bit number. But as our operating systems become, you know, we need to be able to address larger memory spaces, we might decide that the new integer is the old long. And then a long is now a 128-bit value or something like that. These are plausible. All right, so I'll never specifically ask you, like on a quiz or an exam, what's the size of an int, unless I warned you about that specific question ahead of time. I might want you to do math with bits or something, but I wouldn't necessarily ask that specific question. But now that I've given you that information that it's a 32-bit value, or we can think of it as a 4-byte value, right? 8 times 4 is 32. Okay, so a 4-byte value, we're going to need 20 bytes of memory. So we're asking the Java virtual machine to go and find us a plot of land that's 20 bytes big in a row. Okay, that's an important aspect of arrays here, and you're going to see why here in a second. So we need 20 bytes of contiguous memory. Okay, contiguous means in a row. It needs to be right next to each other. And that kind of like works with building a house, right? If we're building a house, if you need 2 acres, you need 2 acres in one place. You can't have a fourth of an acre here and then a fourth of an acre halfway across town. You're just building your house in different places. Okay, so we need 20 bytes right next to each other in order to build a 5-bucket integer array. Okay, so that's what contiguous means. It means in a row. That's an important term. And it's an important thing to remember that arrays need memory that's in a row. All right, so the reason for this is how arrays are actually organized. And hopefully you remember a picture somewhat like this from last semester. Remember something like this from last semester? So I'll go ahead and copy this once, copy this again. We'll change the colors up. We're going to make that red. We'll make that, yeah, good enough. All right, so let's assume our values in this array were like 5, 8, 1, 13, and 2, something like that. All right, so those are the actual values contained in our 5-bucket array as an example. These are the indexes. That's bucket 0. This is bucket 1. This is bucket 2. This is bucket 3. This is bucket 4. Now, these guys are actually memory addresses. So let's go ahead and let's assume that we have, I named it in this previous slide, what, AR? So I named it AR here. So I'm going to say that we have a variable down here named AR. All right. Now, AR is going to have a value. Let's steal this guy. And I'm going to say the value of AR, just to keep things simple, is 100. That's the memory address. Okay? So we're going to say that this guy points to the memory address where our array lives. So this is memory address 100. This is 104, 108, 112, 116. So this is the contiguous memory thing. Okay? So now when we say something like AR at bucket 0 or AR at bucket 2, what this is actually saying is go to the base address of my array. So this is the value stored inside of AR is that array's base address, where it begins. So go to the base address of AR. So this guy is actually AR plus 0 times size of, in this case, int. The size of an int, we said, is 32 bits or 4 bytes. 0 times 4 is what? 0 times 4 is 0. AR plus 0 is equal to 100. What value lives at 100? That bucket is the 5. Isn't that bucket 0? So that's how those guys match up. So this ultimately boils down to the value 5. Similarly, if I go AR at bucket 2, this is equal to the base address of AR plus 2 times size of int, which is 4 bytes. 4 times 2 is 8. 100 plus 8 is 108. Here's memory address 108, which happens to be bucket 2. That's the value of 1 in this case. That make sense? That's how arrays function under the hood. And that's why they need to be represented in contiguous memory. They need to be right next to each other so that this offset stuff works. Because whenever we get to an element of an array, we always start at the base address of the array, where the array begins, and then we offset from there. All right, that makes sense? All right. So now, because of that, what would you say is good about arrays? And the follow-up question is, what's bad about arrays? What's a positive and what's a negative about an array? Go ahead. Okay, is that a positive or a negative?
Can be a negative if you want to add on.
Okay, so one negative about arrays. So negative, they are fixed size, which means we can't add to it without destroying and rebuilding. So that would be certainly a problem in real life. You build a house, you decide you want a porch, you got to knock down that house, build another house that's identical to the old one with a little bit more space in it for the porch. Not going to be real practical in real life. So certainly that's a negative. Okay, what else? Okay. Don't you suspect, you're not wrong, but don't you suspect we probably have other mechanisms in Java that also allows us to hold collections of things? What we worked with last semester in Python was something called a list. And lists actually under the hood don't operate this way. Okay, lists under the hood actually operate in something called a linked list fashion, where they don't actually have to be in contiguous memory. They don't have to be right next to each other. So you're right. An advantage of an array in general is that we can hold collections of things, but it's not our only means of holding collections of things. Now, because we've defined an array of being a fixed size, and because it's created in memory with all the buckets right next to each other, what positive thing does that create for us? Okay? Easy access usually translates into fast access, right? So arrays are fast. We can compute the exact location of an individual bucket of that array by doing memory math. We don't have to go, if we want to get to bucket 2 of the array, we don't have to go to bucket 0, then go to bucket 1, then go to bucket 2. We can just go right to the address of bucket 2. Okay? Same thing's true in real life. If you want to get to the 5th house down the street, you don't knock on the door of the previous 4. You go right to the 5th house because you know that's where you're ultimately going. Okay? So arrays are fast, but in order for them to be fast, they had to be organized in a very specific way, which then became a negative. So the thing that makes them not malleable, if we're going to use they're not as good as strings from that perspective, is also the thing that makes them very fast. Okay? Now, having said that, not to confuse the point, strings are actually implemented as character arrays. That's how they're implemented under the hood. Which is why if we want to change a string, we cannot change a string directly. We have to build a new string. Now, I know some of you have seen the thing that's built into the language called string builder. And what string builder does is it's syntactic sugar for destroying the string and building a new string. It is still destroying it under the hood. It's just giving you a convenience function for doing it so you didn't have to do it by yourself. That makes sense? So, what I mean by that as an example, let's just look at that as an example. If I have a string, and I want to remove this O, that is the thing from bucket 4. This is 0, 1, 2, 3, and 4. So I want to remove bucket 4. Actually, let's go with a different one so we're not stuck with the word hell at the end. Let's go with bucket 1. Okay, let's go with bucket 1. So we'll remove bucket 1 from this guy. If you were going to write the code here to remove bucket 1, what would we have to do? We wouldn't actually remove bucket 1. We would keep everything except bucket 1, right? So could we write a function here? Static string remove at index. This guy maybe takes in an index, and we would pass in a 1 as well as, in this case, a string. In fact, actually, instead of doing it this way, why don't we go ahead and build our own class, because this is going to lead us down the path towards our homework. Why don't we build our own class called superstring, something like that, because we can't name it strings. We already have a string. So we'll right-click, new class. This is a superstring. All right, and a superstring is going to hold a normal string. So we'll have a private string s. When we build a superstring, its constructor will take a string as a parameter, and we'll say whatever string was passed in is equal to our internal string. And then we probably want to have a way of displaying that string. Now, let me actually show you something here. So because this guy is private, he's only accessible within this class, which means that if we want to be able to read the string, we need to give it a getter, some way of accessing the value in there. So we can say public string get s or something like that, and then have this guy return this dot s. That'll give us access to that string, right? Similarly, I think I showed this before, we can actually right-click. If I didn't show it before, I'm showing it right now. Built into Eclipse is a convenience tool for this. This kind of goes back to that discussion we had earlier that computer science folks get these nice tools with all these conveniences in them, where if you're writing stuff for a switch somewhere, you might not have these nice tools. So we have a thing in here under source, generate getters and setters. We'll go ahead and choose the S, and we just want a getter. And let it write it for us. That might have taken more time than it would have taken just to write it by ourselves. But if you had 10 or 20 fields up top, certainly we just saved ourselves time by using the generate getters and setters thing. Okay, but I chose just to get the getter of that. So that gives us public access to a private member of the class. So now I'm going to come back out here to driver. And instead of building string s, I'm going to build a superstring s. And superstring s is going to be a new superstring passing it hello. But then if I want to print out this guy, I'll have to say system.out.println s.getS, which will give me the contents of that superstring. So there's their hello. Now, wouldn't it be convenient if we could just say system.out.println s? That would feel better for us. That's what we're used to doing. But what are we going to get if I just print out s? Memory address, because of this new keyword, right? So that's an object. Objects actually give us memory addresses, and that's what we're going to get. We're going to get the superstring at that memory address. All right, so now what we're going to do here, I'm going to look back at the documentation. We have a function that every single object has. Okay, so what we're really going to start talking about here is this idea of inheritance. So we have inheritance. Now in Java, at the top level, and this is pretty much how all object-oriented languages are built, we have a top-level object called object that just exists in the language. It comes with the language. Okay? It's our primitive object type. Now, we just built a superstring. Okay, so that's one of our guys. Oh, that's handy. So that's one of our guys. Now, when we built a superstring, it actually was built in terms of an object. So there's another invisible thing here. So I go back into superstring. There's something right here that says extends object. We don't see it and we don't need it, but it's there. So this is presumed to be there. All objects, the way that an object can exist is by taking the most generic object and making it something more. That make sense? So there is an invisible extends object in here. We can leave it in. It's not going to break anything. So I'm going to go back to the documentation, or as you put it, the book. It does look like a book. All right, so I'm going to scroll down here. This comes with the core Java language, java.lang. And inside here, we have a object called object. When I click on this, here's our class object. It's a constructor that takes no parameters. And we have a function that comes with all objects called toString. And toString returns a string representation of the object. Is this a class method or an instance method? Instance method, how do you know? No static. So how do we call instance methods? What do you want to say? You want to say this? Oh, surprisingly, both of you are wrong. It's definitely not the class name, but it definitely is an instance method. It would only be this if we were calling it inside of the class in which it was defined. How do we call instance methods in general? Using an instance of the class in which the method was defined. In this case, this method was defined inside of a class called object. So I'm going to need an instance of an object. That is something that is a object in order to call that toString method. So let me show you some more hidden stuff that's out here. When I come into driver and I print out my variable s, I'm actually calling s as toString. We'll see that that's same output. Okay? So what println does, when you call println and you pass it, let me show you how println actually works. So there's a class in here called system that has a this guy right here, out, no parentheses. That must be a field. It's a variable thing. So that guy's a print stream. So we have a field here called out. So go ahead and click on print string, that says type. And then inside here, we're going to find what we should expect is a function called println. We know it's a function because of the parentheses, right? So we should see a function called println. In fact, we're going to see a bunch of functions called println and a bunch of functions called print. So here's all of our prints. And then here's all of our printlns. We have a println that knows how to print a Boolean, a char. Actually, we know how to print a char array. Convenience thing, right? Because I've mentioned that strings are actually implemented as char arrays. A double, a float, an int, a long. And then we have this generic object. Now, we can create, generic objects can be almost anything, right? Any object that we create, we already saw, assuming you believe me, extends object. So that means there is literally an infinite number of generic objects. Correct? Well, how could the people who made Java, Sun Microsystems people, now Oracle, how could they have written a function way back when that knew how to deal with every single object we possibly could ever pass in? They said, look, we're just going to make sure that all objects have a function called toString. And we'll teach our println method that takes an object as a parameter to call the toString method of that object. And it just so happens that the most generic toString method is the toString method that gives you the memory address-y looking thing. That make sense? So if we want the toString method of our superstring class to act differently, what we can do is we can rewrite it. We can override that method. Just like variables, all variables boil down to their most local definition. So that deals with scope, right? Same thing's true with functions. When I call a function, it's going to boil down to the most local definition of that function. It's going to look in the current scope first and say, is there a function right here named this? In this case, named toString. If there's not, I will toss it up to my parent, the next guy in my lineage, and ask him to call that toString method. Make sense? So in our picture here, this dude comes with a default toString. Comes with that function. Now, when I come in here and I say system.out.println s, we've seen that under the hood, that println function that takes in an object I've mentioned calls the toString method of that dude. So the very first thing it does is it's going to look in the current scope here. Do you see a toString method inside of the scope? We do not. Therefore, we're going to pass the buck up to our parent. Who's our parent? Object's our parent. At this point, we're going to start writing things where there's another parent in between, where you might have, grandparents and great-grandparents and so on and so forth. Extend says I am the child of something. I'm extending in an existing class. Okay? So my parent is object. And we've already seen in the documentation that objects do have a toString method. That's the version of toString that it will call. The first time it can find it will be there. Now this is a method that returns a string, and it's called toString. So I'm going to come in here, and I'm going to say string toString, and we're going to go ahead and we're going to return s, which is a string. I'll get rid of that guy. Now notice it's yelling at me here. It's saying cannot reduce the visibility of the inherited method from object. So visibility is talking about public, private, protected stuff. So that's indicating that the visibility of this guy in object is actually public. So we need to throw public in front of this. So we are creating a more local duplicate of that method. It's a method called toString that returns a string, happens to be public because that's the way it was defined. We probably can click on it here and it'll probably show us the public. Yeah, there it is. It's defined as public in here. Okay. So we are overriding this. So I'll put a comment in here. This is override the toString method from object. We are writing our own more local version of that. That make sense? So now just by doing that, this guy's supposed to return a string. What string is he going to return? He's going to return the string that this guy holds. So now when I come into driver, I create my toString, then I go ahead and print out that toString. We're going to see it now shows us hello. No longer the memory address. That makes sense? Super important. This is a top tenner. Okay, very important thing that's going to come in handy. You need to understand how that toString method plays in there. Now, if we also wanted to have the memory address, we can play with fire a little bit here, and we can go ahead and say that inside of our superstring, we'll go ahead and return s, but then let's go ahead and let's concatenate onto that, a parenthesis, I concatenate onto that. What if we wanted our parents, the string that our parent returns for toString? So I want my parents' version of toString as well. I want both. I want to interject my own will in here, but then I also want to go ahead and grab that memory addressy thing. So I need to have a way of calling my parent, talking to my parent. We said that the this keyword is how an object refers to itself from within itself. We have another keyword here called super. Super is how an object refers to its parent from within itself. It's similar to this, but instead of them referring to the object that represents them, we're referring to the object that represents our parent. Okay? Because what actually happened here is when we created a superstring, an object was also created. So we didn't pull everything from object into superstring. Instead, what we said is a superstring stands on its own and then also has a parent called super. That is an instance of object. And we'll pass anything that we can't find locally to super and let him try to deal with it. Okay? So what I can do here is I can go ahead and say super.toString, which is going to return that memory addressy looking thing. Concatenate onto that, the parenthesis. So now I'm building my own version of toString that is built in terms of my parent's version of toString. So I should get my actual string, followed by a parenthesis, followed by crazy memory address, followed by closing parenthesis. Make sense? I'm not sure how helpful that will be that often. But the point here is that you can kind of juggle methods. If you wanted to do something a little bit extra than what your parent was already doing, you can kind of get both. You can do your own thing, but also still rely on your parents. All right, so this is just our first introduction to that super keyword. We're going to use it more often. Not real often, but more often moving forward. But this is just kind of our soft introduction to it. Okay, so we're going to have our superstring class. And now our superstring, I'm going to go ahead and remove that. That way it just prints out what the string is. Now we can kind of conveniently print out superstrings. Now we're going to go ahead and write a function in here. Public void remove at index int index. And what this guy is going to do is we are, as it is right now, because I'm having it return a void, what do you suppose that I'm going to try to do with this guy? I'm not actually returning a value. So what do you think I'm changing? Changing s. I'm changing my internal state. So if I'm a superstring and I'm currently holding a string hello, and somebody says remove at index 1, I'm going to change my version of s to be HLLO. Does that make sense? So I'm going to create a string. Maybe we'll call this guy new s. Start that off as the empty string. We'll loop through for int I is equal to 0. I is less than. We need the number of characters in s. How many characters are in s? S.length number of characters. I plus plus. And as long as we're not currently looking at the index that we want to remove or skip, we're going to go ahead and keep it. So if I is not equal to index, new s is equal to new s concatenated with this dot s dot char at I. The this dot is not required here. I just like using it. It's not required because we are currently, is this a class method or an instance method? Instance method. How do you know? No static. So we don't need this dot in here because we are currently in an instance-based context. So this dot is presumed to be in front of everything. Make sense? Because we are in an instance-based context. I prefer to use it for no other reason than just spelling. When I said this dot, it allowed me to choose s, but s is hard to misspell. Okay, but if I had a more complicated variable name, it maybe would have helped me. So I'm going to say I want to take my variable name s. I want to grab the character at bucket I from that guy, and I'm going to concatenate it onto the current version of new s, storing the result back in new s. After this for loop is done, I've gone through and I have, instead of removing a value, I've kept all values except index. And then what do I want to do? I want to replace my version of s with this new s. That make sense? So we went ahead and we printed out s here. Then I'm going to go ahead and say s dot remove at index 1. This guy does not return a value. I'll go ahead and print out s again. And we see that my superstring has permanently changed. Make sense? So now, what are some functions that would be handy to have in our superstrings? Remove an index was one of them, right? What are some other functions that would be handy? Char at? What else? Index of? Char at would be an index. What about reverse? Now, what should reverse do? Should reverse internally reverse our string, or should reverse return a new superstring that is the old one in reverse? Well, I'm asking you, which is more handy? Keep it internal. So reverse tells it to reverse itself. So this guy reverses the internal state of the superstring. This guy returns the first index of C in our superstring, or -1 if not found. This guy returns the character at position index in our superstring. What else might be handy? What about substrings? Would it be handy to have a part of a string? Maybe from a certain place to another place? Well, if I have hello and I want the substring EL from that, I could say I want everything from bucket 1 to bucket 3, not including 3. So that'll give me the EL. So substring int start, int end returns as a superstring the substring of this string from position. I'm going to kick this down a line. We'll just indent it. Start to end, not including end. Make sense? So if I say give me the substring from bucket 1 to bucket 3, it'll give me 1 to 2 inclusive, not including 3. Okay, so your homework for Tuesday is to write these 4 functions and test them. Sound good? All right, so I'll put this code up on Slack so you have access to it as a starting point, and then I'll put the assignment up, and I will see everybody on Tuesday.